All right, guys, this is our review test. I'm going to be doing the even problems, and once again, the odd ones are included for your benefit. If you want to practice a little more, the answers to those will be included on the last page. So let's begin here. The first few problems are about factoring. So we've learned three factoring methods. There's the Gcf method, and the difference of squares method, and the box method. So we're going to review all of those. So let's begin here. So with the number 2, this is a Gcf method. We're looking for the common factor that we can take out. So in this case, what do all three of these terms have in common? Well, all three of them can be divided by 3. You also want to see if you can take any variables out. Now, in my case here, I can't take any variables out because this last one doesn't have any variables to give. But I can divide all three of these by 3. So I'd be left with 4k cubed plus k plus 4 if you divide that 3 out. And that's what that would look like if you were to take out a greatest common factor. Okay. Let's go ahead and take a look at another problem here. So when it says factor completely, that means that you might have to factor more than once. Or it could be just once, but you may have to factor more than once. Now, whenever it comes to factoring, the first thing you want to do is you want to check to see if there's any greatest common factors. That's always the first thing. Now, I don't think there are any here because the only thing that divides into 9 is either 9 or 3, and neither one of those go into 68. So, and also, they do not all have variables in common either. So, we're going to skip the GCF step here, and we're going to go ahead and move on to the next step, which is looking at how many terms there are. Okay, if there are 3 terms, then we're going to go with the box method for factoring. If there's 2 terms, it might be a difference of squares. Now, on this problem here, we've got 3 terms, so it's going to be a box method problem. So let's go ahead and do the box method. Here's how the box method works. You take that number and you put it in the top left box. You take that number, you put it in the bottom right box. And you go ahead and factor the 9a squared. That's going to give me 3a and 3a. Now, it could also be 9a and 1a. And the box method is really just a method of trial and error. You just do your best and you hope it works out. So let's see if this works out for us. So you may not want to write this until I have my final answer, but it's definitely good to watch so that you can kind of see my thinking process that I go through. All right, so let's do 32. The first thing that comes to my mind with 32 is 8 and 4. Now, one of them has to be negative, so let's go ahead and make the 8 negative there. Now, the next thing is we're going to see if this works, and here's how you see if it works. You fill in the blank boxes. So I'm going to do this box here by multiplying the 3a and the negative 8 together. And so that gives me negative 24a. And then I'm going to multiply this 3a here and this 4 to fill in this box. And that's going to give me 12a. Now, I know that I've done things right. I've got the right choice if these numbers add up to make the middle, and unfortunately they don't. Negative 24 and 12 makes negative 12. So that's no good. All right? Now, I don't think just switching, well, in fact, I know just switching the sign's not going to work. So instead of putting the negative there, you might think, well, let's try putting it here. Well, that's only good. That's just going to make my sign opposite. It's not going to give me a completely different number. So that means I need to change my numbers. Now, there's other things that make 32. There could also be 16 times 2. Let's try that out. Let's try 16 and 2 and see if that works. So filling in my box once again, that gives me 48 and this gives me 6. One of them has to be negative. It doesn't really matter which one I make negative. But I'm still not going to get 68 out of that. So I'm still not happy. We're still not working out here. Let's try changing, instead of changing these ones, let's go ahead and try changing these numbers now. Let's try 9 and 1a. That's another possible combination. All right. 9 times 16, that's going to be 90 and 54. Now, I'm pretty sure that's going to end up being too big. So I think we've already overshot it. Yeah, that's not going to give me 68. So as you guys can see, we're just going through a process here of guessing and checking until we get the right answer. Let's try keeping the 9a and the 1a and the 16 and the 2, but let's try switching the 16 and the 2 around. See if that works. That gives me negative 18 and 16a. That was not working either. Stubborn. So as you guys can see, it's kind of a trial and error process, and we just kind of keep going until we find a pair that works. Let's go back to the 8 and 4 method here. 8 and 4 for 32. Let's try that. 9a times 8 is 72a, and negative 4 and 1a is negative 4a. Do these add up to make 68? And I think we finally have a winner. It's close, but it's still not quite right, because if I combine these, I get positive 68, but I want negative 68. And whenever you have the right number but wrong signs, that's a real easy fix. Just switch the signs. So instead of making the 4 negative, make the 8 a negative. And that just reverses their signs. So now I've got my pair here. It's 9a plus 4 times a minus 8. And that was kind of a pain in the butt. There was a lot of guessing and checking I had to do there in order to get it to work. But unfortunately, that's just how the box method is sometimes. But the goal here is basically find two numbers that multiply to make this number, find two numbers that multiply to make this number, and you know you have a good guess when these diagonals add up to make the middle. So you just have to try different combinations and putting them in different spots until you get that combination that just so happens to work. Let's go ahead and take a look at another one here, number 6. Once again, we start by looking for a GCF first. So the last one doesn't have an R, so I can't take any R's out of there. But I do notice that all of these things have a greatest common factor that you can divide out. And you have to just kind of mess around and see what's the biggest thing that can go in there. And I think the biggest thing that goes in there is 4. So if I were to divide out a 4, I would be left with the following. Okay? And now, for what's left here, since there's 3 terms, once again, we're going to go with the box method here. All right, so we got 10r squared and negative 30 here. We're looking for two things that multiply together to make 10r squared. So let's try 5r and 2r. And then let's try two things that multiply together to make 30. Now I'm going to go with 5 and 6. So I'm going to put the 5 here and the 6 here. And let's see how that works out for us. So that gives me 25r and 12r. And I think I got lucky here. One of these has to be negative. So let's see if that works. Negative 12 and 25, I do believe that makes negative 13. So I just got totally lucky there. And I happened to get the right one that time on my first guess. But there's that. We have 5r minus 6 and 2r plus 5. So here's your final answer. You're going to have your GCF on the outside and then the two binomials that you got from the box method after that. And then you're all done. Let's go ahead and take a look at number 8. All right, so once again, you want to check for a GCF. Do we see any GCF here? There is no GCF, but we can factor this. This has got 2 terms in it. Anytime you have something that looks like this, 2 perfect squares that are being subtracted from each other, you could rewrite it like this. You take the square root of the a, and that's what goes here and here. You take the square root of the b squared, and that's what goes here and here. And you make one a plus and one a minus. So this is fitting that form. We could take the square root of this and get 5x. And we could take the square root of this and get 2. You make one a plus, you make one a minus. Now remember, this only works though if you have a negative sign here. If you don't have a minus, then it's no longer a difference of squares and it actually wouldn't factor at all. But that's the end of that one. So now we've looked at all three methods for factoring. GCF, you always look for a GCF. Box method is if you have three terms. If you have two terms, it could be a difference of squares. Let's go ahead and take a look at number 10. All right, so GCF once again. I do see a GCF this time. Both of those can be divided by 3. After that, I have two terms, and when there's two terms, it could be a difference of squares. Well, I've got the subtraction. That works. And also, both of these are perfect squares. So, we do have a difference of squares here. The square root of 4b squared is 2b, and the square root of 25 is 5. We're going to make one plus and one minus, and no, the order doesn't matter. If you put the plus first and the minus, it's the same thing. But there you have it. So that takes care of number 10. Let's go ahead and take a look at number 12. So we're switching gears now. We're not just factoring anymore here. We're actually going to start solving for r, and that really just adds one more step to the process. We're still going to factor, but there's going to be one more step after that. So step 1, is there a GCF? No GCF. Step 2, 3 terms means box method. So let's head up the box method here. R squared minus 35, R and R, 7 and 5. One of them needs to be negative. Let's fill in our box. These two should add up to make the middle, which they do. And so I've got R plus 7 and R minus 5. But this time it's not just R plus 7 and R minus 5. It's R plus 7 and R minus 5 equals 0. So now here's where the next step comes in. We're going to use something called the zero product property. When you have two things multiplied together that make 0, that means one of those things has to equal 0. So either R plus 7 equals 0 or R minus 5 equals 0. If we solve, we should end up with our result, which is either R equals negative 7 or R equals 5. Okay, so that's how you can solve an equation by factoring. So factor like normal. After that, do the zero product property. Let's go ahead and take a look at number 13. Let's go ahead and take a look at 14. We're not going to do 13. That's odd. We're going to stick with the even ones here. So, let's see. Is there a GCF? I don't think there is. The only thing that goes into 49 is 7. And I don't think 7 divides into 48. So, there's no GCF on this one. So we're going to jump right into the box method. Got 49x squared here and negative 48 here. Now 49x squared, I'm wagering that that's probably 7x and 7x. 48, let's go with the most common guess. I'm thinking it's probably 8 and 6, but we'll have to see. One of them has to be negative, so I'll make one negative. So this gives me negative 56x, and the other box will be 42x. And if I combine those, does that work? Negative 56 plus 42. I think it does. So we have 7x minus 8 times 7x plus 6 equals 0. From there, we're just going to go ahead and set each one equal to 0 and solve. So, on this one, if I were to add 8 and divide by 7, I'm going to get x equals 8/7. And then for this one, if I were to subtract 6 and divide by 7, I would get negative 6/7. Okay. Let's go ahead and move on to number 16. So we're getting away from factoring and solving now. We're going to go backwards, and we're actually going to multiply. So I want to multiply these two binomials together. I'm going to use the box method again. But when you're multiplying, instead of starting inside the box and working your way out, we're going to start outside the box, and then we're going to fill in the box. And there's no guess and check on this. This is much nicer. It's not as iffy and confusing, in my opinion anyway. So we have 21r squared. We have negative 6 as our last term. These two get combined together. 21r take away 6r is going to be 15r. Now sometimes when you're doing this box method, you got to make sure that you are actually allowed to combine these. Like if they're not like terms, then you can't combine them. But in this case they are. They're both r's, and so we're able to combine them. Let's go ahead and take a look at number 18. So this one's a trinomial and a binomial, and we have to make a little modification for that. We're going to make our box 3 by 2 instead of 2 by 2. We're making it 3 spaces long because one of our polynomials here are 3 terms long. Other than that, it's pretty much the same process. So let's go ahead and fill it in. 7a times 5a squared is going to be 35a cubed. 7a times negative 5a is negative 35a squared. 7a times 8 is 56a. Negative 2 times 5a squared is negative 10a squared. And we'll just keep doing this multiplication here as we go. So I've got 35a cubed. That takes care of that one. These two are like terms, so I'm going to combine those. Negative 10a squared and negative 35a squared is negative 45a squared. These two are like terms, so that's going to be 66a. And then we're left with the last number there, which is 16. All right, let's go ahead and take a look at number 20. Oops. All right, so just getting bigger is all. Same process though. This time I've got a trinomial times a trinomial. When you have that, you need to make a box that's 3 by 3. All right, so we've got 5k squared minus 6k plus 6 on the top, and then the other trinomial is 4k squared minus 6k plus 4. And we're just going to fill in our box here. So all right, so starting from the top left corner, we have 20k to the 4th. There's no other terms that have a k to the 4th power. Then these two are cubes, so we have negative 30k to the 3rd power and negative 24k to the 3rd power. Putting those together, we're going to get negative 54k to the 3rd. Notice that you don't change the exponent when you're combining these, right? You just combine the coefficients. Next, we have k squareds, and there's actually 3 of them down this diagonal here. We have 24, 36, and 20. So that's going to be 60, 80k squared if you add all those together. And then next you're going to combine your k's. Negative 36 and 24 is going to be negative 60k, followed by our last one, which is 24. And there's our final answer there. All right, moving on to number 22. We're getting away from polynomials now. We're moving into rational expressions. Rational expressions are really a lot like polynomials, though, because it's just really what happens when you take polynomials and put them in a fraction. So let's get started here. When it comes to this sort of a situation, all we want to do is reduce it. So 24 over 24 reduces to 1 over 1. And v to the 4th power, or v to the 3rd. Now, you can think of that as 4 v's are being multiplied together on the top, and 3 v's are being multiplied together on the bottom. And every time you can divide 1 v by 1 v to get 1. So basically, they kind of just cancel each other out, and you're left with 1 on the bottom and 1 v on the top. And so basically, you have that. Now, the short way of doing this is basically just to take the number of v's that are on the top, which is 4, and subtract from it the number of v's, which is on the bottom, and that will give you your result. So we have 1v left on top, and the simplest way to write this would be v, because 1 over 1 is just 1. Okay? So reduce your coefficients like you would normally reduce a fraction, and then for your variables, you're going to subtract the exponents. And if the bigger one's on top, then that's where the leftover goes. If the bigger one's on the bottom, it goes on the bottom, and that's important because you'd have to put a 1 on the top of it. So like if I had this instead, you don't need to write this, but let's say we had this instead. These still are going to make 1, right? And we're still going to have v to the first power, but this time it's going to be on the bottom. In that case, you have to leave a 1 on the top. Okay? 1 over v is not the same thing as v over 1. So we want to make sure that with the 1 over v's, we leave the 1 on the top. All right, let's go ahead and take a look at number 24. So now when it comes to polynomials, the last one was just a monomial. Okay? Number 22 is a monomial. But number 24 is a polynomial. This thing is going to come about in 2 steps. Step 1 is to factor the numerators and the denominators. So now I'm not going to show my work, but you would use the box method. I'm not going to show my work because we've already done enough practice of that as is. But you would factor these. So the top, using the box method, would give me the following. The bottom, if you factor it, would give me the following. And after that, you're basically going to reduce. So if you see any factors on the top that match factors on the bottom, then they can divide each other out. And so I'm left with a plus 9 over a plus 10. Okay, so factor and then reduce. Let's go ahead and take a look at 26. Multiplication, it's really just more of the same. It's really just more of the same. So let's factor this. Now, it's not a difference of squares. Even though there's a subtraction, you can't take the square root of this. But even if it were, we would still have to check for a GCF first. And there is a GCF there. Do you guys see what divides into both of those numbers? 7 does. And if you divide both of those by 7, you're going to be left with r minus 3. And that one's done being factored. This one down here on the bottom, however, that is a difference of squares. There's no GCF, so we could factor that one. The square root of r squared is r. Square root of 9 is 3. Bring down our multiplication symbol. Here we've got another GCF. We could take a 7 out. Here we've got a box method. All right, so step 1 is once again to just factor everything you possibly can. This was kind of a busy problem because we had to factor everything. Sometimes you only have to factor one of them. Sometimes the numerators and denominators just don't factor. They're just simple expressions. But these ones all could be factored. All right, after that, guess what? The step is the same as it was last time. It's just to reduce. So whatever's on the top and the bottom. Now the reason for that is because when you're multiplying fractions, basically you just do top times top and bottom times bottom. And so basically it just becomes one giant fraction anyway. So long as there's a factor in the top that's also in the bottom, they can reduce each other out. So for instance, the 7s here can reduce each other away. The r minus 3s can reduce each other away. And the r plus 3s can reduce each other away. And all I'm left with here is an r plus 4 on the top and an r plus 8 on the bottom. Okay. Let's go ahead and move on here to number 28. Division's a lot like multiplication, it just has one extra step. And that extra step is to keep, change, flip. Keep the first fraction exactly as it looks for now. Change the division symbol into a multiplication symbol and flip the second fraction over. Okay. After that, it's a multiplication problem. So the steps are the same on this next step as they would be on the last problem that we did. So the first thing we're going to do now is we're going to factor. So what can we divide out of 30p and 48? I think the only thing I can think of that would go in there is 2. So both of those can be divided by 2, which would leave me with 15p minus 16. On the bottom, we have p plus 5. Now, there's no GCF there, and it's not a difference of squares either, so that one's just going to stay the same. But I'll put it in parentheses. This guy here, there's a GCF. I can take a 5 out. And this guy here, I think I can take a 5 out of there, and that would leave 5p minus 8. All right, let's see what reduces out of this thing. And this is a really strange problem. Oh, I see. Oh, I didn't think much cancel. Usually they have a lot of stuff canceled, but in this case, not much. These go away, and the 5s go away. So that's good. So on the top, then, we are left with a 2, and then a 15p minus 16. And on the bottom, we're left with a 5p minus 8. And that would be our final answer there. Now, some of you guys might be thinking, well, Mr. Bailey, can't we divide the 5 into the 15? The answer is no. Back when we did these lessons, I explained to you guys that while you could do A times B over A times C, you could reduce this and get B over C. Why? Because reducing is division, and division cancels multiplication, which is what's going on the top and bottom here. What you can't do is this, though. You can't take a piece of a sum like that and get B over C. That does not work. Don't do that. Okay? Now, if you have something like this, you can reduce the A plus B's because that A plus B is being multiplied with something on the top. So that's okay. Okay? But what you can't do is take a pair of numbers that's being added or subtracted and only reduce a part of it. It has to be a factor. In other words, something that's being multiplied to reduce. So keep that in mind. Let's go ahead and take a look at number 30. We're moving on to addition. Now, whenever you're adding fractions, you want a common denominator. So we're going to start simple, and we already have common denominators here. So when you have two fractions with a common denominator, you can add the numerators together and just put them over that common denominator. So I took k plus 2 plus 2. And I put it all over that common denominator of 4k minus 12. We can go ahead and simplify this. This is going to be k plus 4 over 4k minus 12. Now sometimes, but almost never, you may have to reduce these afterwards. But that almost never happens, just so you know. On this problem, we can factor the bottom out. But as you can see, it doesn't reduce anyway, so there's no point in doing that. But I just want you guys to be aware, if you see this as an answer, then just stop there and bubble in that choice. If you don't see it, try factoring to see if you can get a match. But when it comes to adding and subtracting, after you actually add and subtract, they almost never reduce, so don't do that step unless you don't see your answer available. All right, let's go ahead and do another one here. Now, I've still got, well, actually, that's there we go. On this one, we still have a common denominator, but this time we're subtracting, and I want to show you the significance of that. We have x plus 3 minus 2 all over the common denominator. Now, this problem doesn't demonstrate it very well, but I will explain. If you had something here like, let's say, x plus 1, you want that in parentheses because you're going to distribute that minus to both pieces in that case, okay? Now, I don't have an x plus 1. I only have a 2. So it's not going to be quite as obvious how important this is, but putting those parentheses is helpful because it reminds you to distribute the negative. But in this case, we have x plus 1 on the top, and on the bottom, we have 7x plus 6. Now, would I see my answer there? I think I would, so I'm not going to factor this, so I'll leave it alone. All right, let's go ahead and take a look at number 34. Okay, now we've got a problem. This is where things get a little more interesting, and our issue is in the fact that we don't have a common denominator, okay? So with these types of problems, the first thing that you're going to want to do is factor the denominators. Notice I'm only saying denominators, though. But factor your denominators. So that's step 1. So I have 6 over, on the bottom, this does not factor. And this one doesn't really factor either, so I guess we're going to skip that step for now. Okay? After you factor your denominators, you're going to multiply to match. We want these denominators to match. So the side over here on the left has a 3a minus 5, and the side over here on the right has a 6a squared. So the side on the left, in order to look like the right, it needs a 6a squared. And whatever you do to the bottom, you do to the top. The right side, in order to look like the left, needs a 3a minus 5. And so that's what I mean by multiply to match. Now, part of this step as well is going to be make sure you simplify the numerator. You don't have to simplify the denominators, but you do need to simplify the numerators. So this becomes 36a squared. The bottom I'm going to leave like this. I don't want to multiply. On this one, we're going to have to distribute that 3a. So that's going to be 9a squared minus 15a. Now, why don't I multiply the bottom? Because the last step may require us to reduce, and to reduce you have to factor. So we need this in reduced form, factored form, so we can reduce it if necessary. The bottom is done. We're not going to do anything else with the bottom, so we might as well just leave it in factored form. But for the numerators, we're not done. We have to actually combine our like terms, and you can't do that until you've simplified these. So I multiplied, and now what we're going to do is we're going to go ahead and combine the numerators. Because at that point, we should have common denominators. So I've got 36a squared plus 9a squared minus 15a. And we can go ahead and combine these guys together here. That's going to make 45a squared minus 15a all over 6a squared times 3a minus 5. Now, because I'm a math teacher and I have a trained eye, I already know that if this was a multiple choice test, you would not see this exact answer. And that's because this one actually can reduce. Like I said, it's kind of rare for these things to reduce, but sometimes they can. So notice that the bottom's already in factored form, but we can factor the top a little bit. I'm going to take an a out of the top there. Matter of fact, we could take out a, I think we could take out a 15a. 15 goes into both of those things. That would be 3a minus 1. Okay. Now, after doing that, we can reduce this monomial pair, just like we did on, I forget what number it was now, but it was our first rational expression problem we had on this worksheet. The 15 and the 6, you can reduce those like you normally would. What goes into 15 and 6? 3 does, right? So if you divide the top by 3, you get 5. Divide the bottom by 3, you get 2. Notice also we can reduce these a's. I've got a to the first over a squared. So if we subtract those exponents, 2 minus 1, I'm left with a to the first power. Since the bigger one's on the bottom, that's where it's going to be left over at. And then we have this and this left over. And nothing else reduces. So this is what your final answer would look like. So this one was reducible. So I'm going to put for step 4 here, reduce with a question mark. And like I said, you only need to do that if it's necessary. Like if you did these 3 steps and you feel pretty confident and you still don't see your answer, try reducing it. That's probably what it is. All right? Let's go ahead and move on to number 36. All right. Another combining of rational expressions, unlike denominators here. So let's put these in parentheses. Step 1, factor the denominators. Now, once again, neither one of those factor. Step 2 is to multiply to match. Now, if you're wondering where this, I wrote these steps down on number 34, so if you didn't see that, you might want to go back and look at it. But the second step is multiply to match. And what do I mean by that? Well, whatever the right side has, the left side needs to have that also. So I'm going to put a p plus 3 here. But whatever you do to the bottom, you have to do to the top. Likewise, whatever the right side has, the left side needs. So we need to multiply the left side by 3p plus 5. And whatever you do to the bottom, once again, you do to the top. After you multiply to match, you should have 2 fractions with the same denominator now. After that, we're going to simplify the numerators. So I need to distribute this 5 here, and I need to distribute this 5p in here. And let's see what we have as a result. 15p plus 25 over and then here we have 5p squared and 15p. All right. So now I've got 2 fractions with the same denominator. The numerators are simplified. We're ready to combine the numerators. So we're going to take the one on the left here and the one on the right here. Notice I've got parentheses. We'll see why that's important in just a second. And we put it all over that common denominator. P plus 3, 3p plus 5. So why are the parentheses important? Because it reminds us to distribute this negative to both terms. So I end up with 5p plus 25 minus 5p squared minus 15p all over my common denominator. Okay, now these 15p's cancel out. And we can also factor a 5 out of what's left there. So now you may not have to do that. In fact, maybe we shouldn't have, because I can see that nothing reduces. So chances are they probably would have just left the top as 25 and 5p squared. But there it is. That's our final answer. So let's go ahead and move on to number 38. All right, so now we're doing a new type of problem where we're going to have rational expressions and we're going to solve the equation. So step 1 is to, once again, factor the denominators. Now, none of these denominators factor, so we're going to move on to step 2. Step 2 is multiply to match. Actually, I take that back. Multiply to cancel the denominator. So I'll show you what I mean there. All right. So I'm going to take this entire expression here, and I'm going to multiply the entire equation by the denominators. So let's start with 5n squared. And I'm just going to distribute this. Now when you're doing this, we're only going to multiply it on the top because I'm thinking of this as 5n squared over 1. So it's only going to go to the top. It's not going to affect the bottom. So I'm left with 5n squared over 5n squared here. 5n squared over n here. And 20n squared over 5n squared here. Next thing we're going to do is we're going to reduce or cancel. So like 5n squared over 5n squared is 1. Anything divided by itself is 1. 5n squared over n is 5n. 5 stays, and the n squared divided by n first leaves 1n on the top. And then the last one here, 20 over 5 reduces to 4, and the n's just completely cancel each other out. And after that, we should be able to solve, and on some problems this step will be simple, on some it might be a little more work. This is a more simple one. To solve for n, all I need to do is minus the 1 on both sides, and then divide by 5. So if you divide by 5, you're going to get 3/5. Now, if you might want to remember, this last step is check your answer. It can't make the denominator 0. Okay, so if you were to plug in 3/5 here, here, or here, would it make the bottoms become 0? No, it wouldn't. So it's a good answer. We're not allowed to have an answer that would make our denominators equal 0. But there's our steps. So, if possible, factor the denominator. Step 2, multiply each factor into the numerator to cancel it out or reduce it. From there, we should be ready to solve. Just make sure you check your answer at the end. Let's go ahead and take a look at one more here, number 40. So, if you didn't see the steps for these problems, go back to number 38. I wrote the steps out there. Step 1 is to factor the denominators. Now, this first denominator does not factor, but this second one does. This has a GCF, so I can take an R out of there. Same thing with this one. All right, step 2 is multiply by each factor in the denominators to cancel out the denominators. So I'm going to multiply by r plus 2, because that's one of my factors, and also by r, because that's another factor. Now let's go ahead and multiply that into the numerator of each one of these. Okay, and then from there we're going to reduce whatever we can. So these cancel out completely, and that leaves 1, just so you know. It doesn't make 0, it leaves 1. Over here we're left with a 3r. And over here these completely reduce each other out, and we're left with 3. So we have a pretty simple equation to solve there. It's going to be 3r minus 1 equals 3. Go ahead and solve. And we get 4/3. Now, if you were to plug in 4/3 here, would that make 0? No. How about here? No, that's not going to make 0. So that's a good answer, and we're going to keep it. All right? So that'll do it. That'll be it for our review quiz for the day. So hopefully that was helpful to you guys, and we'll see you guys in class. Have a good one.